welcome back to my YouTube channel, in which I have created the playlist of data science covering the basic and advanced concepts. So my next topic is dimension reduction. So let's discuss what is dimension reduction. In data science, it refers to the process of reducing the number of features in data set while retaining as much of the important information as possible. This is particularly useful when dealing with high dimensional data, which can be difficult to analyze, visualize, and model effectively due to the curse of dimensionality. Dimension reduction helps simplify complex and high dimensional datasets, making it easier to analyze and interpret the data while improving the performance of models. It is a crucial and critical step in pre-processing for many machine learning tasks, especially when dealing with large or unstructured datasets. So now discuss when to use dimension reduction. First, high dimensional datasets. When there are large number of features, especially in areas like genomics, image processing, or text analysis. Second is visualizing complex data. When you need to plot or visualize high dimensional data, techniques like PCA or DSNE help reduce the dimensions to 2D or 3D for easier interpretation. Third is improving model performance. When dealing with noisy or irrelevant features, dimension reduction can enhance the effectiveness of machine learning models. Now, what are the common dimension reduction techniques? First is PCA, which stands for Principal Component Analysis. It is one of the most widely used techniques. It transforms the original variables into a small number of uncorrelated variables called principal components. These components capture the maximum variance in data. The goal is to retain the most common or important information by keeping the components with the highest variance. Second is linear discriminant analysis, that is LDA. It is a supervised method that reduces dimensions by maximizing the separability between classes. Unlike PCA, it takes class labels into account to find a lower dimensional representation that best separates different classes. And the next is AUTOENCODERS. These are neural network based methods that learn to encode the data in a lower dimension space and then reconstruct it back to the original dimension. They are widely used in deep learning for dimensionality reduction. Now, what are the benefits of using dimension reduction? Improved model performance. By reducing overfitting, models may perform better on unseen data. Second is faster computations. Fewer features mean less computational resources or are needed for training and inference. Visualization helps in visualizing complex high dimension data in lower dimensions, making it easier to understand patterns and clusters. Next is noise reduction. Irrelevant or noisy features are discarded, which can lead to better predictive performance. Now, what are the types of dimension reduction? First is feature selection. It involves selecting a subset of most important features from the original dataset and discarding the irrelevant or redundant ones. Methods for feature selection include filter methods, wrapper methods, embedded methods. Now, second is feature extraction. It transforms the original features into a new set of features, often in a lower dimensional space. Common methods include PCA, LDA, DSNE, autoencoders. Now, let's move to the coding part. I have given the code to demonstrate how you will identify multi-collinearity pattern. First, import necessary libraries, that is pandas with alias name PD, numpy with alias name NP, cborn with alias name SNS, matplotlib with alias name PLT, and import necessary libraries like variance inflation factor, add constant, make regression. And in order to create a regression dataset with multicollinearity, I am using make regress function, in which I am passing the sample and samples equals to 100 and feature equals to 5 and noise equals to 0.1, random state equals to 42. In order to read data in the form of data frame, I am using the format pt.dataframe and store the result in df. In order to show the first few rows of the dataset, I am using head function, and in order to compute the correlation matrix, I am using the core function and storing the result in correlation matrix. In order to visualize a correlation matrix with a heat map, I am first using figure method, in which I am figurizing the correlation matrix in xy axis respectively, corresponding to 10 or 8. And then I am using heat map function, in which I am passing the respective parameters, and then I am using the title function, in which I am passing the title correlation matrix. At last, I am using the show function to show the correlation matrix. In order to add constant, I am using add constant function. In order to calculate the inflation factor, I am using first p.dataframe method, and in order to store features and data index, I am using constant dot columns, and in order to store inflation factor, I am using data with the index VIF. And in order to compute conditional number for the feature of the feature matrix, I am using line and log dot condition function. So now let's discuss how to apply principal component analysis using Python. First, import necessary libraries and packages like pandas, numpy, c1, matplotlib, and PCA standard scalar load iris. In order to read data in the form of iris, we are using load iris function or library. And then in order to feature matrix, we are using iris.data. In order to target labels, we are using iris.target. In order to convert into data into pandas data frame, I am using pt.data frame format and storing the result in df. In order to show the first few rows of the dataset, I am using head function. In order to standardize the data, I am using standard scalar function and scalar.fit transform method. In order to apply PCA, I am using PCA method in which I am passing number of components equals to 2, and PCA.fit transform in which I am passing as x scaled parameter. In order to convert the pieces into data frame, we are again using the same format, that is pt.data frame function and storing the result into dfpca. In order to visualize the result, I am using the same functions, that is figure, scatterplot, title, showing the title of PC of iris dataset, x label showing the principal component of 1, y label showing the principal component 2, and then at last showing using show function to show the result. So this was all about my topic, dimension reduction. Thank you for listening me patiently.